Hi, Dave Alwell here. This is Lab 4. I'm going to run through this pretty quickly because I'm trying to catch a plane in exactly 2 hours, and I want to get this up before I get on the road. We're going to try and do a couple things in this lab. First, we want to look at generating random data, both using a spreadsheet and using software. Secondly, talk a little bit about goodness of fit statistics, and a little bit more importantly about interpreting curvature in plots to understand goodness of fit, which is objective 4. Produce and interpret some failure rate plots, and then we're going to spend a lot of time on number 5, which is randomly generating data under various sample sizes and censoring schemes to see how the precision in the estimates is affected by that. So there's a lot to go here. Let's get started. We'll first start by generating some random data. So hopefully you've opened a spreadsheet and you have one in front of you, as I do here. I've labeled cells alpha, beta, P1 and P2. Let me just move these up here so they match what we got there. And now I'm going to try and use the spreadsheet to generate some random data. The idea I'm using is that if a probability is equal to a cumulative distribution function of a time, then if I take the inverse distribution function on both sides, then I have the inverse CDF of a probability gives me a time. And it's easily shown that if I put a probability in that's uniformly distributed between 0 and 1, I get a time back out under this process that exactly follows the distribution for the original cumulative distribution function. So in particular, if I take the Weibull distribution and invert it, I get time is equal to beta times this quantity minus log of 1 minus p raised to the 1 over alpha. So how do I get the p? In Excel, I get the p by typing in the rand command, open and close parentheses, and that gives me a uniformly distributed random variable between 0 and 1. Now to do the rest of this, I just need to put my values in. So let's pick alpha equal to 2. Let's pick beta equal to 50. Let's name this cell alpha as alpha. Okay, I've already named the second cell as beta, and let's enter our formula. And this is equal to beta times, open parentheses, minus the natural log of 1 minus my particular time, which is just cell P7, 2 right parentheses, caret, open parentheses, 1 over, and my alpha. For some reason it didn't like the naming of that. So I'm going to put some dollar signs in here so I have the exact formula here. $D, $3, close parentheses, single close parentheses, enter. All right, so if my random variable is 0.13, this is what my random time is. And if I hit the F9 key a few times, I'll get different random variables and different failure times. And that's how the general idea works. Okay, so now if I copy this down 10 times, let's see, 7 up to 6, I get 10 random variables that are drawn from this Weibull distribution. That's pretty easy with these designated parameters. Now if I want to get a little tricky on this, I can censor it. So let's pick a censoring time. Let's pick, what did I say, 30. Okay, so let's say censor equals 30. Our censoring time is 30, and then we can have our censored time as equal to the minimum of whatever time we had, or 30. So if it gets to 30, it will stop. I'm sorry, I don't want to use 30, I want to use this value, and I want to use the absolute address for that, my dollar signs, and close the parentheses there. Okay, so 53 or 30, which is smaller, 30? And then let's just copy this down. And I see sometimes I get the censored value and sometimes I get the real value. In particular, out of these 10 samples I'm running, I'm only getting 4 actual failure times, which isn't very many. If I hit the F9 key again, I can see here I only got 2. This time I got 3. This time I got lucky and got 5 failures, 4 failures, 1 failure, 3 failures, so on and so forth. Problem is, of course, the fewer failures I have, the harder it is to get any precision in my results. And I'm going to need at least 2 failures to plot my line to give me any estimates what's going on a probability plotting point. All right, let's add a second set of data. Okay, in this case, we'll put in another Weibull distribution, this time with 0.8 for the shape parameter, and we'll put in 100 for the scale parameter. And let's put in another P. Here, call this P2, and call this T2. Put a random time in here. And then, again, do the same idea, equals, excuse me, let's call this cell alpha 1, or call it alpha 2, and call this one beta 2. Okay, and do the same thing here to generate our times. And now we have, this is going to be equal to beta 2 times minus the log of 1 minus our second probability, close parentheses, caret 1 over our second alpha. Okay, so here's some times for that, and again we'll just copy this down. So now I've got some times generated from this model with infant mortality because alpha is less than 1. Let's just stop and look at these times. I got a very early failure, 0.2 here, another one at 1. Then I got some 95s, some 140s, some very long survivors. Let's hit the F9 key and just take a look at it again. Now I've got a 2, a very long survivor, 244, F9 again, F9 again. I'm seeing the bounce. All right, let's censor these as well. Also at time 30. And again, same idea, it's going to be the minimum of this time and our censoring time. Close parentheses, and copy that down. So again, I'm seeing very few of the actual times because the censoring is kicking in. And if I hit the F9 key a couple more times, I see that. All right. So for my competing failure modes, I would take the minimum of the two censored times. So that's going to be the minimum of this one and the minimum of this one. And that's the race to see which of the times it fails. And here I get 30, and I run this down. And now with the censoring, I'm only seeing 2 failure times. Here I get 4, and it's bouncing around back and forth. Okay? Sometimes I get a lot of failures, sometimes I don't. So in particular, if I've got high reliability items, I'm likely not to see many items fail early before my censoring time. All right, so that's what I wanted to do, talk about how we do this going through here, and that's how I would do it in a spreadsheet. If I wanted to use a different distribution, I would find the inverse CDF for that particular distribution and do it that way. All right, let me take a break, and then we'll switch over to Minitab and show how we can do this without having to do it by hand and do some data analysis. Hello, I've switched over to Minitab now. I'm going to assume you can get it displayed on your desktop, and I'm just going to start. All right, so to generate data from in Minitab, I can generate from an individual distribution. If I want to do the censoring or competing failure modes, I can also do that, but I'll have to do the minimum to find the competing failure modes. I also want to show quickly how to do a mixture distribution. Then we're going to do some quick analysis of that and see how the standard models don't capture the behavior from either the competing failure model or the mixture model. And I'm going to also throw in a little bit of spreadsheet analysis to show what the failure rate function should be looking like. All right, so the idea here is I go to my calculate menu, down here to random data, over to the Weibull distribution, and then let's calculate 25 of these. I've already gone ahead and named my columns, but put it in the first column here. I have a shape parameter of 3 and a scale parameter of 100. Okay, so I do that. And then notice that I've typed in the name W300 here just so I can keep track of what I'm doing. Similarly, for the second one, I go back to calculator, random data, Weibull, and this time I'll put 25 in my second column, and I will use a shape parameter of 0.8 and a scale parameter of 200. Okay, click that in, and there are those numbers. And you're obviously going to get different numbers than I get, but it's the same general idea. So we've done that and that. And now let's look at a competing failure mode. So the competing failure modes would be the minimum of each of these times. So to get the minimum here, I'm going to go to data. I'm going to go to, I'm going to go calc to row statistics, and then I'm going to get the minimum of, for each row, this row or that row, or those two columns. And what that does is going to take the minimum of each of these two values and put it in here. So let's click that here. I've stored it in CFM. I've obviously rehearsed this. That's why some of the numbers are popping up for me. Open the blank cell, collect on the right column. There we go. Okay, so let's just look. What's the minimum of 103 and 140? It's 103. 167 and 693, it's 167, fine. This is working the way you want to do it. Okay, and so now I've got, from these two independent failure modes, I've generated life data for each of these failure modes, and I've now generated the competing failure mode, failure time, which is the first of the two times to fail. All right, so this is the competing failure mode. Let's just take a look at distribution ID plot and see what it looks like. So let's go to stat, reliability, survivability, distribution right censoring, and distribution ID plot. And let's take a look at our competing failure modes plot. And let's just use our standard 4 distributions we've been using, Weibull, log normal, exponential, normal. Okay, so if I plot these and look, so I'm getting actually better behavior than we made the lab sheet. But I'm seeing exponentials bad. I'm seeing the normals below, above, and then below. That's bad. This log normal is really underestimating my early life. So I'm seeing failures here and here, and it's saying my chance of failure is much smaller. And I'm getting the same thing with the Weibull distribution. When I ran this with the other data set, when I built the lab sheet, it was more pronounced, but the same thing is there. And I also see this over, under, and then converging to the right behavior pattern. Okay, so there's some curvature here. It's not good. And in Minitab, I can't fit a competing failure mode plot to this data. I can't fit a competing failure modes model using Minitab. To do that, I need some specialized software. So that's not too good. But let's take a look at the what the true hazard rate for this model should look like. And I did that in Excel. Here I put in my 3 and my 100, my 0.8 and my 0.2, and for the failure rate, I've got the, I've added the failure rates, which are, it's the Weibull distribution reliability, it's the density function divided by the reliability of the first one, plus the density function divided by the reliability of the second one. The density function I get by putting a 0 for my Weibull distribution command. I get the reliability function by putting a 1 here and then doing 1 minus that. Weibull distribution gives me the failure probability, 1 minus that gives me the reliability. And I add those two together to get my reliability function for the competing failure modes. And I do the, that's not the plot I want the plot down here. Sorry, it used to come up, actually come up to the top. I've done two plots here. I'm getting ahead of myself. Okay, and here is the plot of the reliability. And what we notice, it's a little infant mortality, and then it goes to wear out, which is about what we would expect. Okay, so that's what it should look like for the competing failure modes. Okay, because we know it, because we know the distributions from which this data was generated. All right, so let's go back to Minitab. And let us fit the competing failures mode, fit a Weibull model to competing failures mode and see what we get. Because the Weibull was the best fitting of the bunch. So if I go to reliability, survivability, distribution analysis, parametric distribution analysis, get out of this, go to my competing failure modes. I don't have any censoring here. I want to, on the graphs, I want the hazard plot and the probability plot, my two plots. Okay, let's just see what we get when we do this. Okay, so the hazard plot that this gives me estimates my shape as being about 2. There's no hint of the infant mortality here, and I don't see any hint of the infant mortality in this hazard plot. But what I do see in the probability plot is some indications that there's something going on funny in the early life here, because I'm over, then I'm way under, then I'm over, then I'm getting on. I've got a snake sort of fit here, and that snake fit is generally a sign that I've got a bad model selection. Okay, back to our lab sheet. Notice that when I did it, the first example, I got something that was concave down because I got a different shape parameter. That reinforces the idea that even with a sample size of 25, I'm getting an awful lot of volatility in what the shape of this is. 1.2 to 2, that's a huge swing. We're going to come back to that idea. So the hazard functions don't agree with the true model, and that's a consequence both of the small sampling size, we're seeing the variability, and fitting the wrong model. No matter how big the sample size we had, fitting a standard Weibull is not going to pick up this bathtub problem. One more thought. Let's talk about a mixed population. So remember, the competing failure modes is when one or more failure modes are having a race to see which will be the first to fail. A mixed population is different. That's where I've got some fraction of the items came from one population, another fraction came from another population. Those times are just mixed together. So to do that pretty easily here, let's go back here and label another column mixture, and let us go to our data, and let us go to stack. And let's stack some columns. So let's take I'll delete this so you can see how it goes. Let's take the first column and the second column and just stack them on top of each other and put them in the mixed column. Okay, so that'll give me 25 entries from the first distribution, 25 from the second distribution. Okay, so we'll do that. All right, and here's my mixture. Here's the first 25, and then here's the second 25. All right, so before we go fit a model to this, let's see what the actual failure rate function should be. So the failure rate function for mixture is the sum of the two densities divided by the sum of the two reliabilities. So it's slightly different form, and we've done that here in Excel, where in this cell I've got the first density for density for the first failure time plus the density for the I'm sorry, the density of the first time plus the density of the second time divided by the failure rate for the first distribution plus the failure, gosh, I'm just making hash of this. So I've got the failure rates, the two failure rates in the numerator, and I've got the two reliabilities in the denominator added together. And that's different than what I have for the competing failure modes, but that's how it works out. The point is that the shape of this failure rate plot for the mixture is much different than I've seen for other things. And it's not going to be easily modeled by the Weibull, which is either concave up or concave down. And this is first concave up and then it's concave down. It's really going to be tough. All right, so let's take a look at how this works when we go to Minitab. Okay, so coming back to Minitab, we've got our mixture. Let's fit a, let's take a look at the probability plots for this. We'll go to reliability, survivability, distribution analysis, distribution ID plot. We'll get our standard 4 plots again. And we see, again, we've got issues with this data set. Although not as bad as with the first data set. We've got some problems with bad fit for our early times on both the log normal and the Weibull, huge problems with the exponential, and problems with the normal as well. Why do we care about this tail? Well, most of the time when we're doing the liability data, we're doing it to set a warranty time. That's the standard choice. And here, if the failures are actually occurring at a higher percentage than the model suggests, we're going to lose money on our warranty. Not such a big problem here because we're seeing failures at a lower rate than the actual model would suggest, but it's still something to be concerned about. All right. So of the 4 models, I'm looking at my correlation coefficients. The one with the biggest correlation coefficient is generally preferred unless there's some compelling reason not to. So in this case, it's the Weibull model. So I will go back to my data and I will fit a Weibull model to it. Stat, reliability, survivability, right censoring, parametric distribution analysis. I'm now using my mixtures. I want to fit a Weibull model and we'll click OK. And what do I get here? So here I get, for my hazard rate, I get concave down, and I know that's not the same shape as I saw in Excel. What did we have in Excel? We had this, and that behavior is completely missed in our estimated model, which we knew that would happen. And secondly, when we look at the data, we're seeing a whole bunch of curvature in this data, a whole bunch of curvature. In fact, I think what I did for the, let me go back and look at this graph. I may have not hit the distribution ID plot. Yeah, I didn't use the mixture stuff. I had the wrong thing set. So let's click on this and go back and do that again real quick. Yeah, so now for our mixture, when we actually look at the mixture data, we're seeing this huge curvature, all these really bad effects, and none of these models looks to be very super, although the log normal looks to be a little better in this particular case. But I'm going to continue to fit the Weibull just to make my point. So if I go back for my Weibull model, clearly the data doesn't fit the probability plot. That's horrible. Okay, if you ever see a plot that disagrees, has that much curvature, it screams to you, I don't have the right model. And then the next, oops, cancel. And then the next thing I see here is that my failure rate for the mixture is not capturing the behavior I know should be there. In fact, my it's asymptotically going to go back, the failure rate's going to go back down to 0, and this doesn't capture it. But that's one of the reasons why the log normal actually is not a bad fit here, and was suggested, because if I fit the log normal distribution to this, and then I do get something that head backs down to 0. It doesn't have quite the right shape, but it has better asymptotic properties than the other one. Okay, so what I want to take away from this, when I've got this pronounced curvature in the probability plot, my model's likely wrong. And second, when I've got poor fit in the lower tail, that's of concern depending on what I'm using the model for. If I'm doing it for warranty work in particular, then this is going to be a big problem. Okay, this concludes this portion of the lab. I'll be back. All right, I'm back. I was having a little trouble with the paste between my Mac and my Windows machine, so I entered the data here by hand into this folio, folio 2. So now what I'm trying to do is to show what utilities we have to help us choose which model to pick. So there's, in Weibull++, there's something called a distribution wizard. So if I select this, it will look between these various distributions to decide which are the appropriate ones I should be using for the model, which best fits. Let's go ahead and take all of the possibilities and click Analyze. And it goes through and it ranks all of these distributions from 1 to whatever we have here. Now what's going on is that there are 3 tests under the hood that I talked about in week 4. One is a goodness of fit Kolmogorov-Smirnov, which measures the distance between the empirical cumulative distribution function and the fitted cumulative distribution function, takes the max of the difference. The second is this from the plotting plot. It looks at how linear the plot is using that Anderson-Darling statistic that we saw calculated in the Minis tab output. And the third is the value of the likelihood. If I use the likelihood statistic, if I pick my maximum likelihood estimates, there's an underlying value for that maximum likelihood for each model here in the log scale, and it shows which of those is the biggest and scores that. That's what it does initially. Then it ranks those, it weights the different ranking methods and comes up with a score, and the low score wins. Okay, and so what do we end up with here? We end up with the reported recommended distributions. Okay, in the example I worked in the class, things went, in the lab worksheet, things went a little bit better. And we ended up with the 2 parameter wobble being the best, which is fine. But we'll go through and do this again. Okay. But I just wanted to show that's one way to get these possible values. The other thing is that when you only got 4 data points, it's going to be very hard to know which to use, which model to use, because there's not a lot of precision, and you're not going to put a lot of faith in whatever you get. Just to show how Weibull++ works, I don't think we've been through this before. Let me just say I choose a distribution to fit here off of this list. I'm going to choose the 2 parameter Weibull. Notice I have the mixed Weibull, a bunch of other choices here. To do a competing failures mode model, though, I need to know which of the populations, which of the failure modes generate a particular failure. That can be hard. We won't do that today. But to fit my 2 parameter Weibull, I hit this little parameter button here, and it calculates the parameters for me. And here I've got a beta of 1 and an eta of 56. Remember, this was from a competing failures model, and what it's doing is giving me back basically exponential distribution. A couple other nice features: if I hit this plot button, I will get the probability plot, and again with 4 points, it's hard to tell what's going on. That generates on a different tab. If I go back to the original tab, I also have this quick calculation parameter, QCP, which allows me to say, calculate these values. For example, what's my reliability after 50 units of time? It's estimated as 41%. I can turn on my lower one-sided confidence balance here again, 90%. Calculate that. It's estimated as 41%, but there's a 10% chance this could be as low as 16%. Again, not surprising from the small sample size. I can do conditional reliabilities. I can do put in a reliability and find the associated time. I can get bounds on the mean life. I can get estimates of what the failure life is at a particular time. And usefully, I can get bounds on what the actual parameters are. So for example, here for my shape parameter, remember Weibull uses beta for the shape parameter. It's between 0.56 and 1.8, which is between a lot of infant mortality and almost linear wear out. So you really can't tell from a small sample size. That's my point. Okay. Close out this quick calculation pad. A handy utility. I want to do something else here while I've got Weibull++ open. I want to talk a little bit about simulation. Okay, so let me insert a Weibull++ Simimatic tool here, which is what I've talked about before. And let me look at a model where I'm going to generate data with 2.5 for my shape parameter and 100 for my scale parameter from the Weibull distribution. Let me say I'm not going to have any censoring with this. Let me say I'm going to do 100 data sets, and each data set is going to have 10 points to it. 10 points in the data set. I'm not going to touch this, I'm not going to touch this, I'm not going to touch this. Okay, let me go back and just hit the generate button and show you a graph that results. Okay, so this is my data. Now I hit my plot button, and this is a plot. Now what I have with this heavy black line is the true model that I used when I created the data set. And what I have here from these samples of size 10 is models that have been fitted to 100 different samples of size 10. What does this tell me? Well, let's just look at the time that we could estimate 10% of the units would fail by. This is this red line. And it's going to be as low here as 2 units of time, and it comes over here to 85. So my time by which 10% of my items fails varies between 2 and 85. That's almost, that's over a factor of 40. Similarly, if I want to know what my reliability is at time 5, 9, 8, 7, 6, 9, 8, 7, 6, 5, it could be 0.2%, or it could be as, my probability of failing could be as high as 10, 20, 30, 40, 50%. So from 0.2 to 50% is my estimated chance of failing here at time, what did I say, 50. Okay? So it's going from here to here. Lots of variability. There's no precision in this data. I had 10 failure times, but I have no precision in the data. My model's all over the place just by chance. And this is what you should be able to show a decision maker when you've got a small sample and you're trying to make a high stakes decision from it. You got to really understand there's so much variability here that it's hard to deal with. Let's do another one of these. Let's go back up here to Insert, Semimatic, and now let's just change the sample size to 40. Because remember, to double my precision, I need to quadruple the sample size. And let's run it again. Okay, and let's take a look at the plot of this new data set. And now I'm seeing much more precision. My 10% line is narrower, and my vertical line is narrower. Okay, so that's what these extra 30 units have bought me. They've bought me, they've protected me against the chance I'm going to have some wildly strange results just by chance. And similarly, I can go back again, Insert, Semimatic, and do this again with 100 data points. And fit my plot. And now I'm getting much tighter results. I have much more confidence, much smaller. My confidence bounds are going to be much smaller. All right. And that's basically what we've been talking about here in the lab. Now I want to go back and look at what happens when I do some censoring in this. So let me go back, insert another one. Let's go back to 10 data points. And let's say that they're going to be censored. There's 2 types of censoring. Censoring after a certain number of failures or censoring after a specified time. Let's say we're going to censor it after 5 failures, after half of the items have failed. Okay, we generate this, which means we've only got actually 5 failure times and 5 censored times. Let's look at the plot of that. Wow, there's really not a lot of useful information here. You know, the time by which 10% fails can go between 10 and 80. And look at how much range I've got here in my failure probabilities, from 0.1% to 60% for some of these times. Just no certainty here with the small sample size, and the censoring makes it worse. Okay, let's do another one. Insert, and let's go back and do the censoring now after time 20. I'm sorry, after 20 units, which will be half of our 40 units. Now again, we've got an observed 20 failures here. And we've got the plot that goes with it. It's a little bit better, but again, there's an order of magnitude difference in my estimated probability of failures for early life. Almost 2 orders of magnitude here. Really no precision. And again, one more. This time we'll do our censoring not based after a specific number of failures, but we'll censor it all after time 50. Okay, and we'll go back and do 10 units here. 10 points rather. And we'll look at the plot of it. Look at how many of these NAs, those are where I'm not getting enough failures to even plot the data. It's kind of alarming. And look at this graph. I mean, it's just literally all over the map. Small sample size, no good with the censoring. And let's repeat that just one more time, except let's make it with 40 points. So I'm putting 40 units on test. I'm going to look at how many failed after 50 hours. And I do my plot still all over the map because this censoring early is not letting me see failures, and I need failures to actually know what's going on. And there's a couple other combinations listed in the lab sheet. That's sort of what I want to, once you get out of this lab. I don't want the lab to run forever, but I want you to be able to see that you can easily put the wrong model on a complicated data sets. The software doesn't even have the capability to fit in Minitab competing failure modes or mixed models. Just can't do it, okay? So plots are important to help you see what the possible problems are. We're looking for curvature, snake curvature. We're also looking for big departures in the tails, particularly in the left-hand tail, early failures, if we're trying to set warranty times. Curvature, if I'm just looking for a mean life, may not be a fatal problem unless the model is overestimating the probability of failure in the right-hand tail, and then I get some long survivors that can mess things around. But curvature always tells me that I probably don't have the right model. And lastly, what we ran through is the importance of the sample size, the sensor scheme, and precision in being able to do these reliability estimates. They really make a difference. All right, so this was a fast lab, a lot going on. I'm assuming you're able to work the software issues out by yourself, installing it. We'll talk about this a little bit in our week 4 class when I'm broadcasting from Newport, but I gotta go catch a plane. Have a great day.